And we ended up with discussing two perfect tensors. One is a 4-index perfect tensor with bound dimension 3 that comes from the 3-Qubit code that we discussed in the first lecture. And we also had a 6-index perfect tensor with bound dimension 2. So now I can use these two perfect tensors to write down essentially two variatory models, one of which we already discussed, but let me write them down in a slightly different way. So the first one is the 3-Qubit model, and the 3-Qubit model was originally written down as 3 physical qubits on the boundary and 1 logical qubit in the bulk. So this was the interpretation of how this is analogous to ADS-CFT. So instead of writing down this picture, we will just use the tensors and connect these points. And the bulk point is now represented by a dangling leg of the tensor. And the tensor is sitting in the middle. So we have one perfect tensor here constructing the 3-Qubit code. Similarly, we can use the second perfect tensor, the 6-index one, to construct another code which involves 5 qubits. Encoding 1 qubit. And again, we have one bulk point. The bulk point is, has a perfect tensor with 6 indices. 5 of them go off to the boundary, and 1 of them is a bulk index. So in both of these two pictures, the way we should think about them is that we have some bulk dangling legs. Here we have 1, here we have 1. They should be thought of as input legs of the tensor. And then we have all the boundary legs. They should be thought of as outgoing or output of the tensor. And because these are perfect tensors, this means we can think of them as isometries from the input, from the bulk input to the boundary output. In particular, as an isometry, this map preserves the inner product of any state that we map from the bulk to the boundary. And turns out this also means we can think of both of these two, and in general, any perfect tensor that we might write down. In this way, we can think of them as quantum error correcting code, where the code subspace, so the code subspace should be thought of as some subspace of the boundary Hilbert space. In this case, the boundary Hilbert space is the space of 3 qubits. Here we have 5 qubits. In general, the code subspace is simply determined by the image of the bulk input leg, the image of the image of the mapped T on the input. The input is simply the Hilbert space of the bulk input legs. So this is a subspace of the boundary Hilbert space. So instead of saying H bulk, I should just say H bulk input. So, so we can now see various ways of reconstructing operators. A lot of the discussion will be similar to what we had seen so far with the 3-Qubit code, but I wanted to use the tensor language to make it more obvious. So the way to do this is we have some operator. Let's say we have some operator O that acts in the bulk. We can then push the operator to the boundary because T is an isometry. So in particular, we can push the operator O to all three boundary legs, and therefore we recover an operator O tilde that acts on all the three physical qubits. So let me write it down here. So in the tensor language, what we're doing is we have some O acting on the input, and then we have a tensor T. T has a total of 4 legs. 3 of them are going off to the boundary, and we're pushing the operator to the boundary by constructing an O prime. An O prime acts on the boundary qubits. So we have been calling this O tilde. Let's call that. Let's keep that notation. This is essentially the global reconstruction. This is analogous to what we do when we use HKIR on the global ADS space, and we get the representation of a bulk operator on the whole CFT. So we can also, this is a picture supposed to be for the 3 qubit case, but by adding 2 more lines, I can make it also for the 5 qubit case on the right. Now we can also perform the Ringer reconstruction. The way to do this is, the reason that we can do this is because T is not just an arbitrary isometry, it's actually a perfect tensor, and now we are going to use that. So let me draw that picture again. So here we have some input that acts on the bulk dangling leg. We can, instead of pushing that operator through all 3 outgoing boundary legs, we can just choose 2 of the boundary legs and call them the boundary leg, and call them the output, and think of the 3rd one as an input. And if we do that, we will push the operator to only 2 of the 3 boundary legs. In the tensor language, what we're doing is we have an O, and we have the same T, but instead of thinking all these 3 lines at output, we only think of 2 as output, and the 3rd one is another input. So we're pushing an operator which is O times an identity operator on this leg through this tensor. And T is a perfect tensor, so this is also an isometry. And the statement is we can find an O tilde on the other side, which acts on the physical qubits. So this is just a rephrasing, or another way of looking at what we have done in the previous lecture. And in particular, we can find O tilde 1, 2, O tilde 2, 3, and O tilde 1, 3. We can also do the same thing for the 5 qubit case, or qubit case. It's essentially the same thing. We have 5 boundary points and a tensor with 6 indices. And instead of pushing the operator, we can have a global reconstruction where we push the operator O acting on the dangling leg into all 5 boundary legs. But we can also push the operator to a selection of boundary legs. In order for the tensor to be isometry, the outgoing or the output legs need to be at least 3. So we need at least 3 output in order for this to be a valid isometry. So we simply choose any 3. One choice is simply to do this one, and this one. And that's analogous to the Rinder reconstruction in this case. We're simply representing this operator on these 3 qubits. So there's a similar equation using the tensor notation that I can write down. I won't do it here. But the interesting thing is I don't have to choose these 3 boundary legs as being 3 continuous ones. I can choose the following. So let me draw another picture. This is exactly the same tensor. We can choose to push 2 of the tensor legs to be this and the other one to be here. Okay? The perfect tensor means the fact that we have a perfect tensor means any division of all 6 indices into a group of 3 and another group of 3 is a unitary transformation. So I can map the operator to these 3 outgoing or output legs. So this will give something which is remarkably similar to the entanglement wedge reconstruction. I have not yet defined the entanglement wedge, but for the purpose that we're discussing now, let me loosely define the entanglement wedge in ADS CFT in using the following example. So we have a time slice of ADS CFT, and we have a region which is the union of 2 disconnected disjoint regions, A1 and A2. So we're considering the union of A is the union of A1 and A2. The entanglement wedge of A is, for appropriate choices of A1 and A2, is going to be this big region bounded by these 2 geodesics. So this is very similar to a region A1 containing those 2 qubits, and the region A2 that contains this 1 qubit. We could have chosen the other 2 geodesics, but the rule is that we always choose the set of geodesics which is the shortest. So when A1 and A2 are big enough, the dominant one is the solid geodesics, and that defines the entanglement wedge. So we'll say more about that later on, but here we're just noticing that we have this interesting way of doing another type of reconstruction of some operator at the center. So as I mentioned before, here we've discussed now one more example of toy models of holography by changing the 3-qubit model to the 5-qubit model. But they're both very coarse-grained. Both of them have only 1 bulk point, a few boundary points. So let's remedy that. In order to remedy that, we're going to introduce a network of these tensors. Now that we know the ingredients to use, we can just tile them by tiling uniformly some nice space. For example, the hyperbolic space. The hyperbolic space is a time slice of ADS, so let's start with that. And we will be using a tiling that we will certainly use perfect tensors. So let me try to draw a picture. This is one of the most difficult pictures to draw in the lecture, but I'll try it. So we have a time slice. Think about this as hyperbolic space. I'm going to draw a 2-dimensional picture because this is a 2-dimensional blackboard. We're going to start in the middle, just like what we have over there, and we're going to use the 6-index perfect tensor. So we start with a point in the middle. That's the 0th layer, if you want. And it has to connect to, we're going to use a 6-index tensor, so it has to connect to 5 points. It has 5 contracted legs. So let's write down the second level. And in this picture, each of the bulk point, each of the tensor would have a dangling leg. Okay, just like over there, I won't actually draw the dangling leg because that would make the picture too busy. So just remember, every point has actually a dangling leg coming out of the board. Now this is the second layer, and we can draw a third layer. And this is where things get more tricky. It turns out that one can get this by using some symmetric tiling of the hyperbolic space. And in this case, it's the so-called pentagon tiling of the hyperbolic space. Okay, so at the second level, means the 5 points that I introduced after the center, now all the legs are being contracted correctly. So the third level here is actually a boundary layer. The third layer is going to be a boundary layer. I'm going to cut off my joint. You can continue on at exponentially cost, but I'm going to, for the sake of terminating this graph, I'm going to cut it off. So all these things will end on the boundary. Sorry? Yeah. It's too small for my purpose, and I cannot draw over there. So let me reproduce it. And you can notice the difference between that drawing and my drawing is much less symmetric. But don't take that for having any physical significance. One just needs to make sure that each index have 5. So each point has 5 legs going out of the on the board, because one of the 6 is coming out of the board. Okay, I assume I didn't make a mistake. So this is using a 6-index tensor, a perfect tensor, to build. This is a so-called holographic pentagon code. And I should mention that this, it's not complete. It's, you can ask, what is the symmetry of the tensor network? It turns out in this particular case, the symmetry it enjoys is the same symmetry as the graph, if you think about this as the graph. The reason for this is because the 6-index tensor that I constructed in a previous lecture this morning has a cyclic permutation symmetry for 5 of the 6 spins. So 5 of the legs enjoy a cyclic permutation. I'm going to use that 5 to be these 5. This is the most symmetric choice that preserves a lot of symmetry, so that's the natural choice to do. The outgoing one, at each vertex, I have a bulk dangling leg. That one doesn't, that is not on the same footing as the contracted legs, but that's okay. So a theorem that can be proven is that this pentagon tiled network defines an isometry from the bulk to the boundary. So all the bulk points have one dangling leg coming out, and we have a larger number of boundary points. we should think of this in the same way as a more complicated version of that. And this defines an isometry just as in the simpler example. So the way we should understand this is we can organize, so just to motivate why this is true, we should think about all the tensors as organized in layers, as I discussed when I drew the tensor network. So that we have, let's say this is the first layer, then the second layer, and the third layer. And the layers are organized by graph distance, essentially counting how many legs you have to, what's the minimum number of legs you have to traverse in order to get to the center. Okay? And a fact about this network is that each tensor has at most 2 legs contracted to the previous layer. So if we consider this tensor, it has just 1 leg contracted to the previous layer, or the others are to the next layer. If we consider this tensor, it has 2 contracted to the previous layer, but no more than 2. This is a signature that we're dealing with a graph on a negatively curved space. Now, we already have at most 2 contracted to the previous layer, and on each tensor, we also have an input just coming out of the dangling leg. So that means the total number of input for each tensor is going to be less than or equal to 3. And this means that the tensor, each of the tensor, can be regarded as an isometry between its input to the output. The input is both from the bulk dangling leg and from the previous layer. Now, each tensor is an isometry. The whole tensor network is simply a complicated contraction of them. And remember, products of 2 isometries is still an isometry. So this means the whole tensor network. So this proves the theorem. The whole tensor network defines a big isometry that maps all the bulk legs to the boundary legs. Okay, so on the same picture, I'm going to reuse this picture because it takes a while to draw. I'm going to give you also how the various reconstruction works. So let's, for simplicity, just reconstruct the operator at the center. We can, of course, do some global reconstruction. That's not a surprise. We can also do Ringler reconstruction, just using the same kind of argument we had previously. We had an input, we have some operator O acting on the dangling leg coming out of this tensor, which is invisible on this graph. And we can push that operator to any 3 outgoing legs because this is a perfect tensor. So we can just choose 3, for example, like these 3. And then we can go forward and forward. Eventually, we will have some big region where this operator O tilde is supported on. So that's like a Ringler reconstruction. We can also do a entanglement wedge reconstruction. In order to do that, I'll simply decide to start by using these 2 output legs and this output leg, just as what we've done previously. And then I can follow through. For example, this input can be pushed to, so I can push the operator successively through the network to the boundary. So that's the idea. We start with an operator at the center. The first thing to do is to push it to an operator supported on these 3 contracted legs. And then for each one of them, I'm going to further select how to push it out to the next layer. So for this one, I'll choose 3. For this one, I'll choose another 3. There are many choices here. I'm making a specific choice, but that's okay. And finally, we can push it to the boundary by choosing 3 for each arrow. I'm just making some choice. Hopefully this is easy to understand, even though maybe the font is too small for it to be visible. But here we do the same thing. We have to choose 3 outgoing. We do something like this. So this is an entanglement wedge reconstruction. It's constructed on the union of 2 disconnected regions. Each region by itself will not be possible to reconstruct the operator at the center. That's something that we can show. But combining the data from 2 of them, we can get the operator at the center. Okay. So in the previous discussion, we discussed states outside the code subspace, and I interpret those states as black hole microstates. Here we can do exactly the same thing. Even though we have a network of tensors and things are more complicated, that makes the physics more rich. So what happens is we can simply remove, let's say, part of the tensor network. One way to remove that is to simply erase 1 point or 1 or more point. Let's first do 1. So we remove 1 point and replace it with a black hole. Here we're just removing the tensor in the middle and reinterpreting these 5 legs they are no longer contracted. We're reinterpreting them as some bulk input legs. So in doing this, we have gone outside the previous code subspace, because the input here does not have to be the specific kind of input that produces the states that we previously discussed, the state in the code subspace. So these have the interpretation of states outside the code subspace, and also it's very natural to identify them with black hole microstates. We can make the black hole bigger by removing more layers. We can even remove the 2nd or the 3rd layer. We can move the black holes a little bit to the side. It doesn't matter where it is located. So we can change the size and position of the black hole by doing this. And the whole point is that we can just remove part of the network, and that makes more states. So several comments about this. The first is that now we have the tool to discuss how the entropy of the black hole scales with the size. So the first comment is the entropy of the black hole, which is equal to log of the number of the states that we're discussing. And of course, the more part of the network that we move, we have access to more states, because we have more freedom to feed in various things in the broken legs in the bulk. So the number of black hole states is bigger, but one can check this systematically and show that this scales correctly with the horizon area in agreement with the Bekenstein-Hawking formula for black hole entropy. And the second statement is as the black hole grows, we can reconstruct fewer bulk operators. And that should be obvious because the black hole is eating more and more tensors. Each tensor comes with a bulk index. One should think of them as some bulk local field. And as the black hole grows, it swallows all those dangling legs, leaving behind fewer things that we can construct outside the black hole. And eventually, if we think about a really big black hole, we can make the black hole as big as it can in this tensor network. What that means is, so eventually, if we do this to the extreme, the black hole removes all the contracted legs and removes all the tensors. We're simply left with a unitary. So a one-to-one map between the bulk and the boundary. The network is essentially gone. We just have a one-to-one map between the bulk state and the boundary state. So in some sense, this is in agreement with what we expect from ADS-CFT. We have said before that ADS-CFT is an exact duality between two sides, two theories. And that in particular means all the boundary states need to have some sort of interpretation in the bulk state. And here we're saying, yes, that's true, but almost all of the boundary states are actually big black holes. Yes? Temperature much bigger than 1 over the radius of the sphere size on which the CFT is defined.
No, much bigger than that, right?
Much bigger than that, yes. Of course. Much bigger than that, yes.
But there's the UV cutoff that needs to enter in that. That's right? That's sort of the size. There's an infinite distance between the black hole horizon and the boundary.
Unless we introduce a UV cutoff. You're right. If we introduce a UV cutoff in the CFT, that's essentially put a radial cutoff in the bulk. And this is trying to saturate that. Yeah. Yes?
The number of space grows like the area
Yes.
because of the geometry of hyperbolic space.
Yes. Yes.
So it's very different from usual black holes. That space.
Yeah, here is because it is related to the hyperbolic space.
So area and volume is the same. You're counting the points and it grows like the area, you can say volume.
Yeah, but yes, there are, so we can debate about how much of a strong evidence this turns out to be, but here what I'm trying to emphasize is that it works in this specific case. Yes. Although probably we should call it a Bekenstein-Hawking formula at the moment. Oh, I haven't yet got to that. Let me get to that. Oh, yeah, yes. 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 Let me get to that now because that's what I'm planning to do next anyway. So we've talked about how bulk reconstruction manifests themselves in this very nice tensor network. And we can actually talk about also the entanglement structure of the state that the tensor network produces. And that's quite important because part of the understanding of the ADS-CFT involves understanding this Rutakianagi formula. So let's discuss that. In general, we can talk about things beyond the entanglement entropy, but the simplest diagnostic of the entanglement structure here, I'm going to use the entanglement entropy. So in ADS-CFT, we all know that we have the Rutakianagi formula, which is the statement that if we have some region A, we can find a minimal surface or extremal surface in the bulk, which is homologous to A, and the entropy of A is simply the area of the minimal surface divided by 4G, and the power Planck M Planck or L Planck goes in there. So gamma A is extremal surface homologous to A. So that's the Rutakanagi surface. I'm going to give it a triangle because I'm going to refer it to a moment. So one comment, let me first make one comment. In the tensor network, in the tensor network that we have constructed, the perfect tensor network, RT is exactly satisfied only in special cases. I won't go through the details as to why this is the case. I'll give you the special cases where this is shown to be exact. The special cases involve the situations when A is a connected region, so it's not a union of two disconnected regions. And also, at least in terms of actually knowing it's exactly satisfied, it is true in a slightly different variant of this version of the tensor network, where instead of having the hyperbolic space tiled by pentagons, we can tile it by hexagons. And when we tile it by hexagons, we have each vertex is contracted with 6 neighboring. Each vertex is contracted with 6 neighboring vertices instead of 5. That means we're not left with any dangling bulk legs, but that means we're just constructing a state. Instead of constructing a map, we're just constructing a state. We can call that a holographic hexagon state. And in that state, we can calculate the entanglement structure, we can calculate the entropy, and the statement is for connected region A, at least we're guaranteed to satisfy the Rutakanagi formula. And instead of talking about an extremal surface, we will be talking about some minimal cut on the graph. The boundary region will be simply a collection of boundary indices or boundary degrees of freedom. So in general, in other words, in a more general case, RT is only approximately satisfied. Yeah, that just means the power of 1 over g is still correct, but there's some fudge factor that we may have to insert to make it right. So the question is, can we do better about this? And this naturally leads to a second kind of tensor network. So the answer to this is yes. We can actually find another type of tensor networks that satisfy the Rutakanagi formula better, in a more exact way. And as is always true for many other aspects of life, random is often simpler. And even sometimes perhaps better than perfect. So we will use random tensors. So we are already seeing in the past 2 days the SYK model, which is also a random model. So we should not be afraid about talking about random stuff. So the idea is, in the context that we're talking about, is to replace perfect tensors with random tensors. And the random tensor unlike a perfect tensor, it doesn't have to have an even number of indices. Each of the indices can have a different range. They don't have to have the same bound dimension in general. Once we form a network, each tensor the tensor on one vertex doesn't have to be the same tensor on a different vertex. They can be totally different. We can randomly choose them draw them from some probability distribution. And in fact, it's nice to draw them from some natural distribution. Which is the distribution that you get by requiring it is invariant under arbitrary unitary transformations. So that's a very natural distribution to use, and when we say random tensors, we will be drawing from that distribution. And furthermore, we are going to replace the very uniform tiling of the hyperbolic space by something much more general. So it can be any graph in general, and it's got some bulk indices and bulk dangling legs and some boundary dangling legs. So that's the idea. It's very general. We don't have to commit to a particular kind of network. So let me draw a picture. Let me draw a picture of what this might look like. For whatever reason, it turns out I'll draw a network with 8 boundary vertices, and I'll connect them. This shouldn't be thought of having some interesting symmetry. They're just simplest example that we can write down, maybe. So each vertex should be associated with a random tensor. And we have also some bulk dangling leg, in this case 2, that defines the bulk state. So the bulk state, we can feed them with some bulk state, and it gives out some boundary state. So just like in the previous case, this is a map from the bulk to the boundary. And this defines, so the first comment is that this actually defines some sort of holographic mapping, and in the large D limit, where D is the bound dimension of all these tensors, the contracted ones and also the boundary ones, it can be thought as a quantum error correcting code, just like in the previous perfect tensor case, and it implements various reconstruction of operators. So in particular, it has the analog of the Ringler reconstruction, entanglement wedge reconstruction. So it has all the good properties that we discussed before, and furthermore, it satisfies the Rotakianagi formula. So let me talk about how that happens. So for this discussion, so the idea is now we want to consider, let's say, some Rayleigh entropy on some region A, where the region A is a boundary region. We choose, for example, in there, out of the 8 boundary indices, we can 8 boundary vertices, we can choose part of them, 4 of them, for example. And we want to calculate this. And I'm going to assume so without loss of generality, we can always make sure that each tensor has only one, has at most one dangling legs, because we can combine them if they have more than one. We're also going to assume, for simplicity, that all the bound dimension on contracted indices and boundary indices are the same. And we denote that by capital D. So in general, they could be different, but we want to keep things simple. This doesn't modify the physics too much, so let's assume they're the same. So now we can do some calculation. The second Rayleigh entropy can be thought of as minus the log of two partition functions, the ratio of two partition functions. The first partition function, which I've called Z1, is can be thought of as the trace of rho A squared. And the second is simply trace of rho squared. So if rho is properly normalized, then this is just 1. We can forget about this. But sometimes it's useful to deal with non-normalized density matrix. So that would be useful in some discussion. The idea is that we want to calculate this not just for one specific realizations of all the tensors. They're chosen randomly, so a specific realization will be complicated. But we want to average over the distribution that the tensors are drawn from. So we want to calculate the average of S2. It turns out that instead of calculating the average of the log, it's useful to instead calculate the log of the average. And in the case of large D, where the bound dimension is large, the fluctuation, the difference between these two quantities is small. So we can approximately calculate log of Z1 average divided by Z0 average. Yes?
Are you putting an upper bound of the number of legs each tensor has?
No, there's no intrinsic bound. You can have 100 legs if you want.
I mean, on your probability distribution. Otherwise, you're drawing random tensors with a random number of legs.
I didn't make one thing clear. The graph is a fixed graph. So what you would do is you write down the graph. It doesn't have to be random. We're not randomizing that. So we choose a particular graph like that one, and then we're only randomizing the choice of tensors on each vertex. So it's randomizing that state. You can think about the tensor as a state. It's randomizing the state on that Hilbert space. Any other questions? Okay, so we're going to calculate this approximately by calculating the average of the partition functions, Z1 and Z0, and then taking the log. Turns out Z1 and Z0, the average of Z1 and Z0 are easier to calculate. Remember that when we calculate the second Rayleigh entropy, we are talking about the Z1 and Z0 are really partition functions on a doubled system. So we can think about them as replicating the system by a factor of 2, and it can be thought of as a partition function on that system. Without going to too much details, we can do this calculation, and when the dust settles, Z1 bar turns out to be given by the partition function of a classical ferromagnetic Ising model. The Ising model has an action, so the partition function of a classical Ising model is a sum of spin configurations weighted by e to the minus the action computed for each spin configuration. And the action, so it's a tool for calculating this partition function, but it's a useful tool. The action for this Ising model can be written down in the following way. And let me explain that the formula. So what are we doing here is we're associating a Ising spin, a classical Ising spin that takes value plus or minus 1 to each vertex. And the sum here is over all the edges of the network where x and y can be thought of as nearest neighbors, or x and y, the two vertices of the graph, are contracted. X equals boundary means x is a boundary point. So what are the boundary points in here? If we go back to this example, we have 8 boundary points because they are connected to a boundary leg. And we have many nearest neighbor contracted legs that we have to sum over here. What this is saying is for each contracted leg in the tensor network where the two spins on two vertices do not agree, there is an energy cost. There's an energy cost of log d. And now there's the question of what this hx is. Hx is a boundary field that sets the boundary condition. It's a classical field that takes the value of plus 1 if x is in the complement of A, and takes the value of minus 1 when x is in A. So remember, we are separating all the boundary vertices into two groups, A and A complement. So let's do one separation here. We can separate A to be the left 4 points on the boundary, and the right 4 points can be A complement. So these 4 points belong to A. So let's choose that separation. And hx would be some boundary condition that is minus 1 here. So minus, I guess, means spin is down. And up on A complement. That's hx equals plus 1. And finally, a comment about this is the formula for the action that I've written down here the formula for this applies when the bulk state that we are feeding into the tensor network is a direct product state. So let's consider that situation first. We're going to take the large D limit. And in this limit, it's like the very low temperature limit of the Ising model. At low temperatures, the spins will try to agree with each other and form different domains. But they cannot be, all of them cannot be in the same orientation because part of the boundary condition is down, the other is up. So what they will do is try to find a minimal domain wall that separates the up spins with the down spins. So what will happen in this specific case is all the left vertices, so Sx is defined on each vertex. For each of the left vertex, it will be down, and each of the right vertex on the right of the graph will be up. And the domain wall is a cut in the middle. So let's define the domain wall as gamma A. In a large D limit, this is dominated by the lowest energy configuration. And the lowest energy configuration gives a penalty of log D times the length of the minimal cut, which is how many times it cuts through the tensor network. In this case, it's 3. So that is the calculation for Z1. In this particular way of writing down the partition function, Z0 is calculated by doing everything in the same way, but setting a different boundary condition that says the boundary field is 1 everywhere instead of being -1 on some part of the boundary. So in this case, the calculation is very simple. The minimal energy configuration is simply all the spins will be up, and there will be no penalty in the action, and that means Z0 will be just equal to 1. So finally, we find that S2, when we have done this average, is to very good approximation given by log D times gamma A, the size of gamma A. So this is very similar to RT, the Rutakianagi formula. Let me make a few comments about this. Oh, I should also mention that the reference. This is all of this about the random tensors given in the paper by Hayden, Dazami, Chi, Thomas, Walter, and Young. So the first comment is going to be that we can This is the second Rayleigh entropy, but the Rota-Kannagi formula talks about the entanglement entropy. So in order to calculate the entanglement entropy, what we usually do is not stop at the second Rayleigh entropy, even though it may be the simplest thing to calculate. We want to get all the Rayleigh entropies and then perhaps analytically continue. So the first comment is that we can actually do the calculation for the, all the higher Rayleigh entropies. I certainly won't repeat that, but the statement is similar. We can calculate Sn and take the average, and it is also equal to log d times the size of the minimal cut. The second comment is that up to now, the discussion involves only when the bulk state is a direct product state. In some sense, that's the simplest case to discuss, but it's not that hard to introduce a different, more general bulk state. So we can feed, for example, in here, we have two bulk dangling legs that we can feed a state into. We can feed any state we want. It can be a direct product state. It can also be an entangled state. In the general case, what will happen is we will have some correction to the action of the Ising model. The correction to the Ising model will take the form of the entanglement between the two sides of the domain wall for the bulk dangling legs. So in terms of the formula, we find when everything settles, that the Rayleigh entropy would be this plus a bulk Rayleigh entropy that is obtained by first looking at the bulk state. So that's called rho B. That's the state that we define on these tensor legs, for example. And then we take we trace out everything outside the domain that corresponds to A. So in this case, it's the down domain. So EA is the downspin domain. We trace out everything outside this EA. We get a density matrix for the state on EA, and then we calculate its von Neumann entropy. Oh, we calculate its Rayleigh entropy. It means that so when I feed this into when I feed a state, when I say I feed a state into a tensor network, what I mean is take this tensor network and either think of it as a map that acts on some particular state that is defined on the Hilbert space on these two tensor legs. So it's a direct product Hilbert space from, of this Hilbert space times that Hilbert space. A direct product state is simply a direct product space in that Hilbert space.
So the boundary state is still highly entangled?
Yes, the boundary state is highly entangled. It's just a statement about the bulk state. Similar to in ADS CFT, you can pick out the spin in the entanglement wedge and pick out another spin outside the entanglement wedge, and you can ask whether they are entangled or not. Here we have the same thing. Okay, so now we have the Rayleigh entropy, and we have a very powerful formula. Before I do that, let me first just mention that the domain that contains all the down spins is fairly reminiscent of the entanglement wedge of A. That is also determined by the Rota-Kannagi minimal surface in the ADS CFT scenario. Perhaps calling it E is not that a surprise. So now we can take the von Neumann entropy limit, take n goes to 1, and this is trivial to do, and we find the von Neumann entropy is equal to log d gamma A plus a bulk von Neumann entropy Now, this is very similar to RT, the Rutakianagi formula refined by quantum corrections. So, in the ADS CFT setting, we choose some boundary region A. We look at an extremal surface gamma A, and the entropy of A is to leading order in the expansion in Newton's constant, or in the language of the boundary theory, in leading order in the 1 over n expansion, given by the area of the extremal surface. This is the term which is 1 over g. But then we can ask, how does the quantum fields in the bulk contribute to the entropy? And the answer, as was shown by Faulkner, Nokoitz, Malasena, is that it is given by the bulk entropy. The bulk region that we should be considering is precisely the entanglement wedge between the region A and its minimal surface. So this is a bulk entropy. And it's very similar to what we get in the random tensor network. I should mention that these results are very general in the sense that we don't constrain A to be some special region. A can be either a connected region or a disconnected region. It can have multiple connected components. We don't constrain the graph to be tiling of very symmetric space like a hyperbolic space. The graph can be essentially anything you choose, but you may, for various reasons, want to choose it for a triangulation of some nice space, but the result doesn't depend on that. So in some sense, this works for all choices of boundary regions and for all choices of the state. Choosing a hyperbolic space with no perturbation is like choosing a vacuum, but Rutakianagi formula knows more than that. It knows that it works even for excited states and for any region. So this is very powerful in the sense that it agrees with what happens in ADS CFT. However, in some sense, the random tensor networks satisfy the Rutakianagi formula too well, in the sense that it satisfies it when it's not even supposed to, from an ADS CFT perspective. So it is supposed to satisfy the Rutakianagi formula for the entanglement entropy. But for the Rayleigh entropy, the ADS CFT prediction is much more complicated. It's not given simply as some minimal surface area in a gravity context. Here, what we are finding is that all the Rayleigh entropies, including the second Rayleigh entropies, are all given by the same minimal surface area. There are things we can do to change the coefficient a little bit, but it doesn't avoid the problem that if we have, for example, two regions, then the Rayleigh entropy seems additive when the two regions are sufficiently far apart. Yes?
Is there a way to get for one region to get the n plus 1 over n?
You can change the network. and you can get it. So you can get the right independence if you want in 1 plus 1 dimensions. But again, that doesn't change the doesn't solve the problem when you have 2 intervals.
What is this result? Does this result apply to small d?
No, this is only in a large D limit. In this, there are corrections. So for example, in the Ising model, we're supposed to sum over all spin configurations. And when D is not large, we have to consider fluctuations of the domain wall. So that will create corrections to the formula. And I believe this is discussed in detail in their paper. In the gravity, if we translate how much the corrections are, we should think of log D as being similar to 1 over G if we compare these 2 formulas. So roughly speaking, if we have any large N gauge theory on the boundary, then log D is like N squared. And the fluctuation contributes, a fluctuation in the Ising model contribute corrections that are powers in D. So exponential in log D. So those are things which are exponential in N squared. So in the stance of ADS-CFT, those are fairly small corrections that we can safely ignore.
I'm just wondering whether all the Rayleigh entropy are the same, whether that persists, or if you have not large.
Certainly the result will be changed once D is not large anymore. But again, it will change in a way that is not obviously going to solve the problem I mentioned.
Yeah, but are all the Rayleigh entities the same or not?
They'll be different. I believe so.
Also, you said that only in the D goes to infinity limit is a quantum correction code. In the finite T, it's not a quantum correction code?
It's approximately so, but for example, we can write down conditions for it to be a quantum error correcting code, and we can see this, the condition is satisfied when D is large.
So what kind of condition is violated?
For example, we can actually one way to understand there are many ways to understand what condition is being violated. One of the simplest thing I can say is that one of the conditions for having a quantum error correcting code, one of the conditions that we have come to understood that allows us to reconstruct operators in the so-called entanglement wedge comes from the satisfaction of the Rutakian-Nagy formula refined by quantum corrections. So if this is not going to be satisfied away from the large D limit, then you can see that there's going to be issues. These statements about quantum error correction and bulk reconstruction will be away from will be approximate. Yes? So here, I probably mentioned it somewhere during this discussion. So D goes to infinity means the contracted legs and the boundary legs will have large bound dimension. But the bulk dangling leg will still have a different bound dimension, which is not going to infinity. So the condition that you're trying to violate is never violated in this limit. Any other questions? Okay, so in summary, this summarizes the discussion about tensor networks. We have discussed 2 kinds of tensor networks. They both lead to holographic quantum error correcting codes and share very good properties of ADS-CFT. But now, in the remaining time, I'd like to return to ADS-CFT and talk about how the various things we have seen in the tensor networks tied together in the gravity language. So in ADS-CFT, so now I'm going to talk about the bulk reconstruction and how far we can go. So the question I want to pose is that in the first lecture, we've seen how to use the so-called HKIL formalism to get to reconstruct operators in the causal wedge. The question is, naturally, if we have some boundary region A, what is the maximal bulk region that we can describe or we can construct from A? In particular, can it exceed the causal wedge that we have achieved so far? And the answer is yes. And it's the entanglement wedge WE of A. So let me make a few comments about this first. So I'm giving you the upshot because I only have about 15 minutes. But it shouldn't be surprising because first, the tensor networks that we have seen so far already have this reconstruction in the entanglement wedge property. So we shouldn't be totally surprised that ADS-CFT can do this as well. But on the other hand, we should be a little surprised because what this means is that entanglement wedge in general generally contains the causal wedge for the same region. And in general, it's not equal. And by that, I mean they're equal in special cases, very symmetric state, very symmetric region. But besides those very special cases, in almost all other cases, they're not equal. The entanglement wedge contains more space-time region, bigger volume, if you like, than the causal wedge. So what that means is we can actually, from some boundary region, we can reconstruct physics not just in front of the horizon, because the causal wedge is bounded roughly by some kind of horizon, can be black hole horizon or some Rindler horizon, or the analog of that. But we can really go behind the horizon. So this should really be thought of as a new form of subregion duality. It's different from the old HKIL paradigm. And this more powerful version allows us to probe physics behind horizons. So those are the general comments. But let me, well, I haven't even defined the entanglement wedge yet. So I draw a picture. We have seen this picture a lot of times already. And the entanglement wedge of A is supposed to be the bulk domain of dependence. That means the domain of dependence calculated in the bulk of the so-called homology hypersurface. Let me call that H. And a homology hypersurface is in turn defined as an achronal surface in the bulk whose boundary is the union of A with its extremal surface. So this is supposed to be a time slice. and we can choose a homology hypersurface to be this surface between A and gamma A. And then we're supposed to take the domain of dependence of this hypersurface in the bulk. So that defines the entanglement wedge. Very good. The statement is, so we can show that for any operator OA, a little a, acting on the entanglement wedge of A, there exists an operator O capital A that's supposed to be a CFT operator acting on the boundary region A such that the two operators OA and O little a have the same action on the code subspace. Remember, from the lessons we've learned about ABC puzzle, the different ways of constructing operators should be thought of as, reconstruction in general should be thought of as working on the code subspace. So here we are constructing the operator in the entanglement wedge. We should also apply the same rule of asking that the reconstructed operator have the desired property when it acts on the code subspace. Just to be really explicit of what that means, it means OA acting on some state phi is equal to O little a acting on phi, and the same statement holds for the Hermitian conjugate when phi is in the code subspace. So how do we understand this statement? Well, I'm going to not go into too much details, but draw a diagram to illustrate how this works. So we have to go back to the Rho-Takayanagi formula refined by quantum corrections. And where we wrote it down as SA equals, so now it's useful to be more careful about the two terms that contribute. The first term is the area term, but we're supposed to calculate its expectation value carefully in the theory, in the bulk theory. And then there is the bulk entropy term that we discussed previously. So one comment about how we're supposed to understand this. Here we're taking a state, we're tracing out capital A bar on the boundary. Think about it as a boundary state and then calculate the Van Neumann entropy. Here we're taking the same state but view it as a state in the code subspace, and the code subspace factorizes into a code subspace, a part for little a over there and the part for little a bar. And we're supposed to trace out little a bar, get a density matrix for A, for little a, and calculate the Van Neumann entropy. So that's why one is called the boundary entropy, the other is the bulk entropy. And this intuitively means that rho A, rho capital A, which is the boundary density matrix, has some information already about any bulk excitations in the entanglement wedge. Because if you create an excitation in the entanglement wedge, it's going to change the bulk entropy, and this is reflected in the entropy of the boundary density matrix. So boundary density matrix has some way of knowing that. And that's not very precise. So what happened is, from this, we can derive what Tom has told us about the JRMS relation, named after Jeffreys, Lukowitz, Malacena, and Sa. And in fact, there are two relations. The first one is the relation about about the modular Hamiltonian. I'm going to write down a slightly different version of it, a single-sided version instead of involving the full modular Hamiltonian. So the statement is when for any state rho in the code subspace, this is the full state in the CFT, we can define a modular Hamiltonian on the boundary and project it into the code subspace just to make sure it's an operator in the code subspace and is equal to some area operator defined on the Rho-Takanagi surface plus boundary modular bulk modular Hamiltonian. So this is an operator equation, and this is the first statement, and the second statement of JRMS is that the Rayleigh entropy, as we have seen previously, for any two states, rho and sigma in the code subspace, the relative entropy, I'm sorry, is the relative entropy on the boundary is the same as the relative entropy in the bulk. So relative entropy is supposed to be describing some distinguishability of the two states. So it's 0 when the two states are exactly the same, and generally it's positive. This is saying, very intuitively, that if we take two states in the code subspace, then they are as distinguishable in the bulk, in the entanglement wedge, as they are distinguishable on the region A, on the boundary region A. Okay, so from this, turns out we can actually prove an entanglement wedge reconstruction theorem, which is this statement. Let me say this statement is the check. So that is the statement. So this is this step is my work with Daniel Hollow and Aaron Wall. I'm not going to go through the details, but it can be done. And finally, to make things complete, I'd like to also point out that, well, the entanglement wedge reconstruction theorem, what it actually means is that ADS-CFT is not just an arbitrary quantum error correcting code, it's a very special one. It's special because any local thing in the bulk is either in the entanglement wedge of A or in the entanglement wedge of the complement of A, because they share the same extremal surface. So that means we have some sort of complementary recovery property for the kind of quantum error correcting code that ADS-CFT is. Complementary recovery is a quantum error correcting code way of saying that everything, that all the information that we're trying to encode is either in the entanglement wedge of A or in A bar. So it turns out that we can complete the circle by showing that any code that satisfies complementary recovery also satisfies the Rho-Takanagi formula. And this is shown by Daniel Hollow. And therefore, in some sense, all these conditions are equivalent. So now you should be not surprised that in the tensor network models that we discussed previously, we have seen all of those, we have seen these things appear simultaneously, and that's because really, if one of them is true, then the other statements are also true. So I think I'm out of time. I'm going to just end with 3 open questions. The first is, now we are guaranteed that we can reconstruct these operators. What is the simplest way that we can reconstruct them? There's some progress on doing this, but can we do it to higher orders in the 1/n expansion? That's an open question. And also we've encountered slight drawback about Rayleigh entropies because the random tensor networks don't necessarily predict the right Rayleigh entropies as in ADS CFT. So can we do something about that? And finally, we'd like to enjoy all these results and understand black holes. And can we do that? So let me end with that. Thank you very much.
Okay, thanks. So we have time for maybe 2 questions.
Say I wanted to study, excuse me, like a bulk that is a quotiented space, like H3 mod some discrete group like Z. Could I do that somehow with tensor networks? Like maybe take some tensors to be identified? Or something else?
You can do many things. One thing you can do is just use the random tensor network to triangulate the quotient space. And from that, if you really want, you can go to the parent space and take a quotient to get back to the quotient space. And there are also possibilities that you can do this, use perfect tensors, although that may depend on what kind of quotient you do. And one example, one thing I didn't mention is you can certainly create some kind of double-sided or multi-sided wormhole solutions, and those naturally come out of these quotients. So you can do that.
Okay, cool. Thank you.
When exactly and why does it matter if the tensor network graph is a uniform tiling?
Can you say that again?
When exactly and why does it matter if the graph of the tensor network is given by a uniform tiling?
In a perfect tensor?
For either or in general?
In a perfect tensor, well, it's because you would like to maximally preserve the symmetry. Maybe this is something I can deflect the question to Daniel. It's very natural to do a uniform tiling of the hyperbolic space, at least when you have a perfect tensor. And now for the random tensor, you don't need to do any uniform tiling at all. So you can do anything you want. You can do a very asymmetric triangulation of the bulk spacetime.
Where's the difference between the random and the perfect tensors that gives you that freedom?
They're very different in the sense that in terms of the random tensors don't really need any symmetry to work, and that's why you can choose any graph, and it always works. And the perfect tensors is fairly more constrained in the sense of how it works because you have to push the things in the right direction. Otherwise, they don't work as they are designed. So maybe there are better answers to why they, before knowing all these details, why they work. But I think having gone through the discussions we had today, it should be fairly clear there are different realizations of the code.
Okay, I think we should stop here because you need to take a bus. But let's thank Xie again for the beautiful talk.